Good afternoon, everyone. Welcome to the Tree Fund's noontime webinar. My name is Brian Kane, and I would like to give a presentation today on a project that we worked on, funded by the Tree Fund, of course, that was working with the folks you see listed here, my grad student, Ari, and my two colleagues, Nick Brzee and Mike Cunningham-Minnick. I'm going to acknowledge a few other helpers on this project in a couple of slides. We were interested in understanding whether advanced decay detection techniques provided information that tree risk assessors could use to refine their assessments of likelihood of failure due to decay. So here's the publication. It's in a journal called Forests. Before I get going with the presentation, just to acknowledge several very important contributions. Certainly the Tree Fund, we were lucky enough to receive a grant, a dueling grant to conduct this work. The Massachusetts Arborists Association has supported my position at the University of Massachusetts for 20 years now. They have provided an endowment. All of the participants who helped us out in this research project. And then in particular, a few folks who were kind of integral to making the project happen, Jim Clark, as well as one of my former grad students, Dr. Dan Burcham, and then a local consulting arborist, Dave Hawkins, who helped with resistograph assessments of the trees that we used in the study. So wouldn't be able to do this kind of presentation without a huge number of people and institutions contributing. And I just want to make sure that everyone knows how much I and Ari appreciate their contributions to making this happen. So one last thing, you probably have learned that I am not giving this in real time. I'm recording it the day before. One of our cats at home has a melanoma. We got an emergency surgery appointment. It's a challenging surgery to do, and I'm bringing her out to the specialist, which is about an hour and a half from where we live. I'm hopefully going to get back in time for the Q&A after this recorded presentation, and I'm really sorry I couldn't be here for the presentation itself. And the next slide will show you contact information. So if I can't make it to the Q&A, please don't hesitate to email questions. And I'm also going to take the list of questions during the presentation that you type into the chat. I will respond to all of those in a separate document so that Bo can share that with everybody. So apologies and thank you for understanding. My email address is bkane@umass.edu. That's the easiest way to get a hold of me. If you are interested in staying current on what's going on at UMass, that's a great way to follow us on those sites. So we'll go through just a really brief overview of the process of decay and then the process of tree risk assessment. And again, a real quick reminder review of the tools that arborists use when they are assessing decay, from the simplest tools up through the most sophisticated or advanced tools, and then review how decay influences likelihood of failure, because that's part of tree risk assessment. We need to understand likelihood of failure. And then lastly, a quick review of the methods that we used in the experiment, and then try to spend as much time as possible on the results of the experiment. Trees get wounded in a variety of ways on a regular basis. So anytime the bark is broken, the cambium, the inner bark, the wood is exposed, that allows the process of decay to start. There are unintentional causes of wounds, like a car, backing up into a tree, or construction damage. There's also the possibility of even making good pruning cuts. So the one image here clearly is some pretty bad pruning, and somebody who doesn't know how to use a chainsaw very well. But even a good pruning cut, like the image you see here on the right-hand side, even if it compartmentalizes well, there's still the possibility of decay. So any kind of wound can cause can cause decay in a tree. And the process of compartmentalization or coated is how the tree responds to that breach of the outer bark. When that happens, the decay process is essentially a back and forth between microorganisms trying to digest the cellular components of the wood and the tree trying to fend off or defend itself from those microorganisms. So when decay is present, it increases the likelihood of failure, whether or not there's a hollow, just because the tree isn't hollow, as you can see on the right-hand side image here. There's plenty of wood there. It's just been really badly decayed. Some of the cellular components have been digested by fungi primarily. That reduces the load-bearing capacity. So either the decay process creates a hollow, and as a result, there's not as much wood physically present to support the loads that the tree experiences, or the wood may still be present, as the image on the right shows, but it is degraded enough that it no longer has the same strength. So it no longer has the same load-bearing capacity. And again, the tree is at a greater likelihood of failure. Risk is the combination of two things: the likelihood of an event happening, and if that event happens, what are the severity of the consequences of that event? So the likelihood of event is also made up of two things, and that's the likelihood of failure, which we're going to talk about today, as well as the likelihood of impact. The likelihood of failure depends on the loads that a tree experiences and its load-bearing capacity. And this is where decay comes in. Decay influences the load-bearing capacity, as we just described. Failure is basically the loads that the tree experiences exceeding its load-bearing capacity. So if there's enough loads, like, it's a really strong wind, or there's an ice storm or a snowstorm, those high magnitude or high amount of loads, they could cause a tree with no defects, no decay, no weak unions. They can cause any tree to fail as long as the loads are great enough. Even what appears to be a structurally sound tree can still fail because the loads have exceeded the load-bearing capacity. When we're doing risk assessments, we're interested in the trees that we believe the load-bearing capacity has been reduced in some way. So we're typically looking for things like decay or other what we would sometimes call defects that reduce the load-bearing capacity. And so even under what we would think of as a normal load, just like 20 or 30 mile an hour wind or a little bit of snow, that might cause a tree that has a reduced load-bearing capacity that's going to increase its likelihood of failure. The load-bearing capacity is basically a function of how big the cross-section is, so how much cross-sectional area of wood there is, and then the inherent strength of the wood that's in that cross-section. So if we go back to this previous slide here, if there's a hollow, obviously there's less wood. So that means the load-bearing capacity can't be as great because there's less wood. Even if the wood is present, like the image on the right, if that wood is no longer as strong as it had been because the wood has been decayed, there's also now a greater likelihood of failure because decay has reduced the inherent strength of that wood. Keeping this at a kind of a really simple level here, there would be a lot more details to provide with both the decay process and the process of tree risk assessment. But for the sake of focusing on the results, I just want to make sure we have a kind of a basic overview of these processes of decay and risk assessment itself. The effect of decay on the loss in load-bearing capacity depends on two factors, and that's how much decay is present, as well as where the decay is located. So the two images that are shown here, this is kind of rough, very rough estimates, but let's say that both of these areas of decay represent, so the image on the right, image on the left, both of those areas decay. Let's assume that they represent a 50% loss in wood. So they're 50% hollow. We're basically saying that the area of decay, or in this case, the area that's hollow, then that's about 50% of the cross section. In the image on the left, the decay is centered right on the pith. So we call this concentric decay. But the image on the right, you can see how there's a bit of a distance between the center of that area and the pith in the stem. So when the decay is off center like that, it reduces the load-bearing capacity more, even if it's the same amount hollow. So this is 50% hollow, 50% hollow, both images. The concentric decay results in a 10% loss in load-bearing capacity. But when the decay is off center, even if it's the same amount, it's 30% loss in load-bearing capacity. So decay influences likelihood of failure because it's reducing load-bearing capacity, and that depends on both the amount of decay and where it's located in the cross-section. Arborists have known about decay potentially causing failures, increasing likelihood of failure for a long, long time, and have developed lots of different methods or tools or techniques to investigate how much decay is present and where it's located. So the simplest tool, obviously, is just looking at the tree and looking for things like fruiting bodies or an open cavity, other things, visual cues that you can look for on the outside of the tree to assess in a rough way how much decay might be present, or just maybe getting a sense of whether decay is present or absent. The next thing, if you wanted to, use a simple tool, there are things like mallets. You can sound the trunk of the tree. You can, use a metal probe to push into a cavity, an open cavity, and figure out the extent of the decay that's in that cavity. You can use slightly more advanced tools like an increment corer, or a handheld battery-powered drill with a small diameter bit that you can push in and assess the presence of decay based on how much resistance you feel. And then as you start getting into a little bit more advanced techniques beyond then, is using something like a resistograph or using tomography, even radar, to get a sense of what's going on inside of the tree. And the level of sophistication gets you presumably a better inside look at what's going on. So if you're just sounding the tree with a mallet, you can get a good sense potentially of what's present or absent and where it's located in the trunk of the tree. But it's not until you use a drill or a resistograph or sonic tomography that provides a clearer indication of the extent of decay in the cross section. This is basically the impetus for why we conducted the study, was to see how valuable the information you get from using these tools, how valuable that is, and does it change your opinion? Does it change opinions of a bunch of different risk assessors in a consistent way or not? So I'm going to just now go through the basic experimental methods that we used, and then proceed on to the results after that. We were fortunate to have 18 track qualified assessors, tree risk assessors. We looked at 30 different trees, and for each tree, each assessor looked at the tree with 5 different tools, basically, or techniques for assessing the extent of decay. So the first was everybody did a visual assessment of the tree. And then they used a mallet and sounded the tree, sounded the trunk to get a sense of the extent of decay. After that, they examined the resistograph output. So the people who visited campus didn't do the resistograph drillings themselves. We presented them with the output of resistograph drillings, and I'll show you these in a second. And then looking at tomograms, again, these were all done in advance. And then the last assessment was consulting with one of the other participants and discussing everything that they had learned so far up to that point about the tree. Each person gave 5 different likelihood of failure ratings for all 30 trees, and they did them consecutively. So after the visual assessment, they would give a likelihood of failure rating. And then after sounding the trunk with a mallet, they would give another likelihood of failure rating, and so on, so that each assessment was then given a likelihood of failure rating. It wasn't as if people waited until the very end to give a likelihood of failure rating. We used the ratings from the ISA's best management practices. So there are 4 likelihood of failure ratings, which are improbable, possible, probable, and imminent. And the definitions are there. We also assigned a time frame of 3 years. So when you're doing risk assessments, you are assigning a value of risk, and you're also assigning a likelihood of failure value for a specified time frame. So 3 years is a somewhat conventional value. And we'll do each one of these assessments just so you can get a sense of what the trees that they were using, but also the process itself. So, and apologies, some of these pictures are taken when the trees were out of leaf. We did the project in July, so everything was in full leaf at that point. We made sure that assessors first did the visual assessment and only considered defects in the trunk, basically looking at decay. So we had resistograph measurements and we had tomograms in advance of all of these trees. But we wanted to make sure that the assessors didn't think about, like, it looks like there's a weak union up in here. That was not what they were assessing likelihood of failure for. They were only assigning a likelihood of failure value within that 3-year period based on the presence and extent of decay in the trunk. So what is the likelihood of the trunk failing based on the decay that you're going to assess how much is there with these different techniques. So the first one's just a visual assessment. We did remind people to take species into account, as well as like the overall health of the tree, because that will influence, how well the tree is going to grow and compartmentalize. So those were factors for sure, but we just wanted to make sure that the likelihood of failure rating was based on the decay in the trunk, not some other defect someplace else. So after this first visual assessment, each person would give a rating of improbable or possible or probable, and there were no imminent trees, obviously. So the ratings are all going to be either improbable, possible, or probable. So the second assessment is using a plastic mallet, and each person did this individually, sounding the tree, and then again, assessing a likelihood of failure and assigning a second likelihood of failure rating based on the sounding assessment. After that is looking at the output from the resistograph, which is what you see here. Here's the cross-section of the trunk. And then there's a series of drillings with the resistograph that are labeled, and a solid line indicates sound wood, and then a dashed or dotted line indicates the presence of decay. So for each drilling location, there's a little table here that everybody looked at that has the location as well as the ratio of the thickness of sound wood, that's T, divided by R, which is the radius of the trunk. So there's a table here that everybody is looking at, in addition to the visual, the drawing of the cross-section itself. The output also showed the average sound wood thickness, the diameter of the trunk, as well as where the drillings were taken. So the drillings were all taken at the same height as the tomograms so that they would be consistent with one another. After looking at this, everybody assigned another likelihood of failure rating to the tree. And then the fourth level, the fourth assessment is viewing the tomogram. So both sonic tomograms, which is the image on the left, and electrical resistance tomography, which is on the right. There's a percent of sound wood that's listed as the output from the tomography, as well as a percent of the cross section that is damaged. One of the prerequisites of participating in the study, which I'll go into a little more detail in a minute, was that the people who participated had to at least be familiar with tomograms. It didn't mean that you had to use tomography all the time in doing risk assessments, but at least that you knew what they looked like and you knew how to interpret them. So we wanted to make sure that we were getting people who had familiarity with using tools like tomography and resistographs. One other point to add about the tomography and resistograph assessments for the odd numbered trees. So trees were numbered 1 through 30. For the odd numbered trees, after visual and then using a mallet, the participants looked at the resistograph output first, and then they looked at viewing tomograms. For even numbered trees, it was the reverse of that. For even numbered trees, assessors did a visual, then they did sounding with the mallet, then they looked at the tomograms, and then they looked at this resistograph output. The final assessment that people did on each tree was consultation with another participant. So, and we paired people up randomly, so it wasn't the same person all the time that you were consulting with. And then you would talk about what each of you observed on the tree and what you thought about the outputs from the tomogram, the resistograph, the sounding, et cetera. And then you assigned another likelihood of failure rating. So now this gives us 5 likelihood of failure ratings for 30 trees and 18 assessors. Now moving on to the results. This is just an overview of the participants in the study. So out of the 18 people, everybody obviously had tree risk assessment qualification. The average was 6.1 years. We had 7 participants were board certified master arborists, 7 were registered consulting arborists, 12 of the participants had an advanced degree, a master's or a PhD in arboriculture, and everyone, all 18 people, regularly conducted risk assessments as part of their job. So it's not just holding the credential, the track credential. It's also, we wanted to make sure that people were regularly doing risk assessments, as well as I mentioned earlier, they were familiar with reading the output of a resistograph and reading the output of a tomograph. This is experience as a tree risk assessor. So anywhere from somebody who had only been doing risk assessments for a year, even though they had other experience as an arborist, up to people who had been doing risk assessments for 35 years. So the average was 14 years of doing risk assessments, but you see there's quite a range right there. And then the last thing we asked people was how many trees they assessed on an annual basis. And this also was quite a large range, in part because we had some of the participants were municipal arborists, and they did, they might be doing level 1 risk assessments, which would either be drive-bys or walk-bys, looking at lots of trees, as compared to some of the people who were consulting arborists who did very in-depth investigations or risk assessments of a much smaller number of trees. So we also asked participants to indicate how frequently they used the different tools that were part of the study in their risk assessments. So this is not necessarily how familiar you are. Everyone was familiar with using the tools and interpreting the output. But this is asking people how frequently they used each of the tools. So, for example, how frequently do you conduct a basic risk assessment? Almost everybody, 17 out of 18, says often, because obviously that's big part of their job. How frequently do you use a mallet? Again, often. 16 out of 18 people used mallet pretty much all the time. How frequently do you use a resistance recording drill? So only 8 people, so only half the participants used a resistance recording drill often. And there were 2 participants, even though they were familiar with the tool and what the output would look like, they didn't use them as part of their risk assessment practice. And the same pattern is true for sonic tomography. Only 7 out of the 18 people used sonic tomography often. There were others who used it occasionally, but then there were, 6 people who used it either rarely or never. So again, it doesn't mean that they're not familiar with the technology and how to interpret it. It just means that they didn't use it on a regular basis. Quick review of the trees. So remember, there's 30 individuals. The average DBH is 38 inches. The average height, 69 feet. Average spread, 59 feet. So big trees kind of scattered around the UMass campus. And they were in 2 genera, pines and oaks. We had a lot more trees that we could have used, but it would have taken, instead of 2 days, it would have taken 5 or 6 days to do this. So we, limited it to 30 individuals. So in addition to the pines, there's white oak, swamp white oak, pin oak, and red and black oaks. This slide is an introduction to the results, kind of showing the overall pattern. And then I'll go through in more detail each of the different aspects that are listed here. So what factors influenced each assessor's rating of each of the trees? So when we run all these, the data through a statistical model, and I'm not going to go through the details there, but you can read through that in the article, obviously. What factors influenced likelihood of failure rating? So assessment technique, that was, again, visual, mallet, resistograph, tomogram, and consultation. So the assessment technique influenced the likelihood of failure ratings that were assigned. What else? The assessors themselves influence. So this is shows up in 2 ways. One, it shows up as how frequently assessors use tomography and how frequently they used a resistance drill. Those 2 factors we'll go into a little more detail in a second. What else influenced the likelihood of failure ratings? The trees themselves. It's the percent area of decay, which comes from those tomograms, as well as the average sound wood thickness, which comes from the resistograph output. So let's look at each of these factors: assessment technique, assessors, and trees. Let's look at each of them now in a little more detail. So the next several slides are going to look similar to this, and the color schemes are going to look similar to this as well. These graphs show the percentage of likelihood of failure ratings that are either probable, which is shown in black, possible, shown in orange, and improbable, which is shown in blue, for each of the different assessment techniques. So here's the visual, that's the first assessment. Here's the mallet, which is the second assessment. The drill is the third assessment for odd number trees and the fourth assessment for even number trees. And then the tomogram is the fourth assessment for odd number trees or the third assessment for the even number trees. And then the fifth and last assessment technique is consultation. So if you look at the graph, basically what you want to focus on is the thickness of each of these color bands, black, orange, and blue, for each of the techniques, because that's basically telling you what the proportion of likelihood of failure ratings is for each of the techniques. So, for example, for the visual assessment technique, looks like about 55% of the ratings, this is across all of 18 assessors and all 30 trees, more than half of them were improbable. And only, like maybe 4% of all of those ratings were probable. And then there's, it looks like maybe about 40% or so, 35% were possible ratings. So that same pattern, small amount of probable, a larger amount of possible, and then more than half of improbable, that holds for the mallet technique. It's pretty consistent with the initial visual assessment, which kind of gets you the sense that people probably didn't change their ratings a whole lot. We're going to look at that in more detail in a few slides. As you start looking at what we would consider the more advanced techniques, so the using a resistance drill or the tomogram, you can see that there's a little bit more proportion, a greater proportion of probable, but also a greater proportion of improbable. What gets squeezed is the amount of possible for the drill. For the tomogram, now it's changing quite a bit, because you can see the black proportion is like twice as big as any of the other ones. And the improbable, the blue proportion, is a lot smaller. So this shows you that the ratings in general, after people looked at the tomogram, the ratings went up as an overall proportion. There were more probables and fewer improbables. But then, after the last assessment technique, after the consultation, the amount of improbables kind of goes right back to where it started. If we look across, here's that 55% mark. It's basically the same. So after all of the information that people had, they kind of come back to the same proportions that they started off with. Again, this is just an overview kind of all of the different factors, but it is interesting to kind of start thinking about this, and like reading the paper will give you a lot more details, which we won't have time to go through all of that. But let's move on from this and look in a little bit more detail and start looking at these some of these other nuances about the results. So let's think about, okay, how do different assessors, how are they affected by each of those techniques? So the frequency of using tomography, not just being familiar with it, but using it on a regular basis, and the frequency of using resistance drills on a regular basis, definitely influenced how assessors assigned assigned likelihood of failure ratings. So the values, again, we're looking at the proportion of all of the ratings. So it's 18 assessors and 30 trees. Of the people who never used the resistance drill, now remember, that's only 2 people. They have a certain amount of probable. It looks like maybe, 7% of their ratings were probable. 55 or so % were improbable. People who rarely used the resistance drill, a lot fewer improbable ratings, a lot more possible ratings, but not more probable ratings. If you occasionally used a resistance drill, your probable ratings go up quite a bit. Now it's almost 10% of all of the ratings are probable. If you use resistance drill often, there's a much smaller amount, a proportion of probable ratings. The amount of improbable ratings is actually the highest for people who frequently or often used resistance drills as part of their tree risk assessment. So it's over 60%. Looks like it's almost 62%. How about frequency of using tomography for your risk assessments? So people who never used tomography, this was only one of the people who, despite doing risk assessments regularly, just didn't use tomography as part of their risk assessment process. That person came up with, a fair number, mostly possibles and improbables, but still, 6% or so were probable ratings. People who rarely use tomography, about the same, a few more probable ratings. People who occasionally used tomography, most of the ratings were improbable. So almost 60%, like 55% improbable. And then people who often used tomography, same thing, over 60% gave improbable ratings. So there's a suggestion here that being familiar with a technique doesn't necessarily mean that you use it all the time, obviously. And that appears to be influencing how people assign likelihood of failure ratings after using each of these techniques. So doesn't seem like, if you're using tomography, you tend to be a little bit more conservative in assigning likelihood of failure ratings, because you're coming up with more than 60% of improbable ratings. Whereas if you never used it, or if you rarely use tomography, you're less than 50%. You're more like, this is about 47%, and this is probably 45% improbable. So there appears to be a difference there, that this, your level of use with a tool appears to be playing a role. Now let's look at the influence of the trees themselves. And this, remember, is looking in more detail at both the percent decay, which shows up on the tomograms, as well as the average sound wood thickness, which shows up on the resistograph output. There are many more columns on this graph because these columns represent the average sound wood thickness of the different trees. But the color scheme is exactly like it was in the previous slides. What you're, again, looking for is the size of the black, orange, and blue in each of these columns, because that reflects the proportion of probable for black, possible for orange, and improbable for the blue. Just looking kind of in a very broad sense here, you can see that as the average sound wood thickness increases going this way, so this is 17.5 inches of sound wood thickness on average, compared to 5 inches of sound wood thickness. There's, in general, more blue as you go to the right on the graph. As you go back to the left on the graph, with some exceptions, you're seeing more orange, potentially more black as well. So this one tree down here that had only 5 inches of sound wood, more than 50%. So it's like 62% or so of the ratings for that particular tree were probable likelihood of failure. And only, 1% of the ratings were of an improbable likelihood of failure. There are some exceptions, and it's worth just kind of looking quickly at this. So here's a tree that had comparatively small amount. It's still 10 inches of sound wood, but comparatively small relative to, some of these other ones where there's 15, 16, 17 inches of sound wood. Most people, despite the relatively low sound wood thickness, most people, almost 90%, 86% or so, assigned a improbable likelihood of failure. So this is also possible because trees had different levels of exposure. So assessors were looking at the decay, obviously, but they were also looking at the surrounding conditions and trying to get a sense of what the loads might be like, how exposed the tree was. So that also potentially could have played a role. Here's a similar looking graph, lots of different columns representing, in this case, the percent decay from the tomograms. And this pattern is the the opposite of the previous slide, because now as the numbers get bigger, you're looking at more and more decay. So this last tree here is 73% decay. And not surprisingly, again, 50, 60 something percent of people assigned it a probable likelihood of failure. Whereas at the other end, these are trees that showed no decay on the tomogram. The assessment is almost 80% of the people who assigned the likelihood of failure ratings came up with an improbable likelihood of failure rating. And again, that in a general sense, that's what you'd expect. There are, however, as you can see, quite a lot of variability in the blue, for example. It starts out pretty high, but then it goes down. So this is a tree here that only has, according to the tomogram, only has 1% of area of decay. And yet most people, 70% of the assessors assigned it a possible or a probable likelihood of failure. Very few people, only 28% assigned it an improbable. So this gives you a sense, again, that there's a lot of potential conflicting or confounding variables going on. So we need potentially to look at a lot of things in general, and maybe one of the kind of quick take-home messages that you should think about as you practice tree risk assessment is just recognizing that because there's a lot of factors when you are doing risk assessments, even if you're just looking at one defect like decay in one location, there's still a lot of factors that come into play, and people don't, and trees don't always come up with a consistent rating. So now that we've looked at the ratings themselves, we want to get to the question of did assessors change their ratings based on having more information or having new information? So remember, each assessor assigned a likelihood of failure rating after each assessment: the visual, then the mallet, then the resistograph, then the tomogram, and then the consultation. So we want to know, did people change their opinions? Did they assign different likelihood of failure ratings when they got more information or new information from these other assessment techniques? So let's look at it first in terms of the trees, and then second in terms of the assessors. So we've got a different color scheme here, just so we're not thinking about the previous values, because now we're looking at the change in likelihood of failure rating, not the actual likelihood of failure rating. So this dark kind of orangey brown color, these are ratings, likelihood of failure ratings, that increased from the initial visual assessment, okay? And the blue-gray color indicates that ratings stayed the same. So they were not changed from the initial visual assessment. And then the last, this kind of like yellowish, creamish color is ratings that decreased or were less than the ratings from the initial visual assessment. So each of these columns on the graph represents each of the subsequent techniques. So after the initial visual assessment, likelihood of failure rating, then sound the tree with a mallet. Did you change your rating? Okay. So 14% or so increased the rating from the initial visual assessment after using the mallet. But most of the people, the rating didn't change very much. That's this kind of blue-gray color. And then again, about 14% or so using the mallet caused the ratings to decrease. They assigned a lower likelihood of failure rating after sounding the trunk with a mallet than they did when they had just looked at the tree visually. So the same pattern is now going to hold for the next several slides, but we can just look at the columns we're looking at on the current slide. For the drill, it's about the same, 60% or so of the ratings don't change from the initial visual assessment. It's also pretty much the same for the consultation. So this is compared to the initial visual assessment. Did people's likelihood of failure ratings change after they consulted with another participant? And, most people know, most 60% or so didn't change. The rating was the same, whether it was improbable, possible, or probable. It didn't change after the consultation. The only one where it's pretty obvious that there's a difference is right here with the tomogram. There's a much greater proportion of increased likelihood of failure ratings. So it goes from, this is again like maybe 14%, 15, 16%. And then on the tomogram, it's 30%. 35% of the ratings are greater likelihood of failure after people looked at the tomograms. And that doesn't really happen, not to the same extent at least, with any of the other techniques. Let's look in a little more detail now. First, looking at trees that did and did not present some challenges. And then we'll do the same thing with assessors who did or did not present challenges in terms of the rating changing, the likelihood of failure rating changing. So there are 4 trees that had the least number of changed ratings. And then there were 4 trees that had the most number of changed ratings, the highest number. Same color scheme as the previous slide. These are 4 trees, 8, 16, 24, and 29. And we'll look at them in a second. These are the trees that had the fewest number of changed ratings. So the vast majority of each column is made up of this kind of blue-gray color, indicating that the ratings were the same after the visual rating. Here's tree 8. So the visual rating, people are looking at the tree, which is the one in the foreground here. Here's the look at the trunk. This blue and white flagging tape is the level at which the tree had the resistograph and the tomograms done. Here's the output of the resistograph. You can see solid wood all the way through, and the tomogram, same thing. So solid wood is 99%. So most of the ratings did not change for tree 8. Some of them decreased this is from the visual assessment. A small percentage of them increased, but most didn't change with any of the subsequent assessments. Tree 16, basically the same situation. Now, again, remember, you can see this weak branch union right here, but assessors are only looking at likelihood of failure based on decay in the trunk. So the tomogram and the resistograph basically showing no decay. There aren't any visual signs from this perspective, at least, and the mallet presumably also didn't give any indication of decay because the ratings were essentially unchanged from the visual assessment. Tree 24, this is a little bit different. Now, this tree has, based on the blue in the middle of the tomogram here, has substantially more decay than the previous 2 trees. So we're not looking at whether the tree had an improbable likelihood of failure or a probable likelihood of failure. We're looking at whether assessors gave a different likelihood of failure rating after sounding with a mallet or looking at the resistograph or looking at the tomogram or consulting with a peer. So even though there's much more decay in this cross-section, people had a sense based on the visual assessment that there was decay in there. And the same thing is true with tree 29. Again, the fewest number of changes from the initial visual assessment likelihood of failure rating. Here are the 4 trees that had the greatest number of changes from the visual assessment. There are 2 that the ratings increased dramatically, and then there were 2 where the ratings decreased. So a much greater proportion of changes for these 4 trees. 2 of them, most of the changes were increases, and 2 of them, most of the changes were decreases. So the blue-gray is the smallest proportion for these 4 trees, 13, 18, 20, and 28. So for 13 and 18, after the visual assessment, people looked at or sounded the trunk with a mallet and then used the resistograph and the tomogram, and then they did a consultation with a peer, and they said, oh, wow, I'm going to change my rating. I'm going to make it a higher likelihood of failure rating. So 45% of people for tree 13 increased the ratings, and 60% of people increased the ratings for tree 20. So for those 2 trees, what this indicates is that the visual assessment was not sufficient. The visual assessment didn't give people enough information to come up with an accurate assessment. The same thing is true for trees 20 and 28, except it's in the other direction. For both of these trees, the ratings decreased from the visual assessment likelihood of failure rating. So for tree 20, almost 75% of people decreased their rating after the other assessment techniques compared to the visual assessment. And for tree 28, it was 61 or 62% of people decreased their likelihood of failure rating. So let's look at these trees. Here's the ones, trees 13 and 18, the likelihood of failure rating changed as an increase from the initial visual assessment. So looking at the trunk and looking at the whole tree here, there's not too many signs of obvious decay. Again, these are in the winter, so we can't be 100% sure this is what people saw in the summer. But once they looked at the resistograph and then looked at the tomogram, this is cause for increasing the likelihood of failure rating, because there's clearly decay that's shown in both of these outputs. And we should probably see the same thing for tree 18. And in fact, you do. If you look at the trunk and you look at the tree, there's not an obvious indication of a substantial amount of decay in that trunk, but the resistograph output shows quite a bit of decay, which is confirmed with the tomogram, also quite a bit of decay. And that's why people increase their ratings. These 2 trees, remember, 20 and 28, it's the opposite. So people are still changing their ratings, but they are making them a lower likelihood of failure. So tree 20, what I suspect happened, it's got this pretty good lean here. And even though people didn't notice a whole lot of decay, there's a couple, odd things down here. Given the lean, that surely made people think, okay, this has a greater likelihood of failure because of the lean. But then once they saw the absence of any decay through the resistograph and in the tomogram, which both show no decay, it would make sense that most people then would reduce their likelihood of failure rating. And the same thing is true with this red oak. In this case, and I know this tree in particular is one that that I've looked at many times, there's quite a bit of kind of odd growth patterns on one side of this trunk, and it's visually pretty striking. So it would make sense that people would have rated it with a higher likelihood of failure at the visual assessment. But then looking at the resistograph and the tomogram outputs, they don't reveal a huge amount of decay. So it would again make sense that someone would decrease their likelihood of failure rating after using these other techniques. Let's look at how assessors changed or didn't change their ratings from the initial visual assessed likelihood of failure rating. Color scheme is the same. The large area of this kind of blue-gray color indicates most of the ratings didn't change from the initial visual assessment. And most of their trees, less than, somewhere between 75 and 80% of the ratings for assessor number 2 didn't change. And for assessor number 6, about the same. 75, 80% of the ratings were the same from their visual assessment. Here are the 4 assessors who made the most changes from the initial visual assessment likelihood of failure rating. These 2 assessors increased their ratings much more after the initial visual assessment, and assessors 11 and 14 decreased their ratings much more from the initial visual assessment. Probably most importantly is this idea of variability that is influenced by both the trees and the assessors, and to some extent by the techniques themselves. So there potentially a lot of psychology that goes into how one perceives the output of a tomogram or the output of a resistograph. We also, if somebody doing the resistance drillings themselves, that adds a whole nother layer of potential variability that we didn't really investigate. We were just, we gave people the resistograph outputs. We didn't ask them to do the resistographs themselves and then interpret that. The other thing that potentially is valuable, having somebody to bounce ideas off of could be very, very helpful, depending on the situation that you find yourself in professionally, whether you work for a company or whether you work on your own. There seems to be some amount of value in checking with a peer and running ideas by somebody just to get a sense of how clearly you are thinking about the process. That's the end of the presentation. Hopefully there's questions. Hopefully I will be back from the surgeon's office to be able to chat with you and answer the questions. But if not, I will answer all of the questions that were asked as part of the presentation. And also don't ever hesitate to email with questions. Read the article if you want to discuss it. I'm really happy to do that. Thanks so much for your time.